Good morning, everyone. So, today we are going to start a completely different topic, which is cooperative game theory. And hopefully, towards the end, I'll give some pointers to the relation of what we did yesterday to cooperative game theory. But let's first understand what is cooperative game theory, right? So, so far in game theory, what you have done is you have always studied the games where people were competing against each other, right? So you have either you take a two-player zero-sum game where one person's loss is another person's gain, or you basically, even if you take it to other general games, at least they were just trying to maximize their own utility by making the rational and intelligent decisions, right? So that so the focus was simply on maximizing their own utility, and the decisions were more or less conflicting with each other, right? So, but if we really go to the practical scenarios, there are many cases where instead of these conflicting games kind of a scenario, you also need people to cooperate with each other, right? So, can you give me some examples where you think that cooperation is required? Prisoner's dilemma, cooperation is required, but we basically you would have looked at the prisoner's dilemma game with respect to the conflicting case, right? So when they don't cooperate, they end up in doing confess, which results in a very less utility to both the prisoners, right? But we do understand that if prisoners, instead of making the independent decisions, if they would have cooperated with each other, they might have ended up with a better utility. Okay, so that could be one. What else? Public goods, right? So when you want, so any situation where you want the teams to come together and work for something, you need the cooperative game theory, right? So that people are working together, coming together, but there are challenges that we will see in today's lectures. Okay, so coming to the first example, which is the prisoner's dilemma. Let's try to revisit what happened there. These utilities may not be same as what you would have seen in your prisoner's dilemma, but the idea is similar. So you have two prisoners. I will assume rows to be player 1 and columns to be player 2, and the strategies are not confess, not confess, and the idea is basically if the person who is it's reverse, I guess. If the person who is not confessing and the other person gets confessed, so the confessed person gets the utility of 0, the confessed person gets the utility of 6, whereas the non-confessed person gets the utility of 0, right? So the person, this is utility. So I have converted everything to the utility, but the idea is same. The person who is not confessing gets the lesser utility as compared to the person who confess, right? Similarly, the here also the person who confess gets more utility as compared to the person who non-confess, but if they both end up in confess, then the utilities becomes 1, 1, which is lesser than 2, 2 if they would have chose to be non-confess. So let's recap what was the Nash equilibria of this game. Confess, right? It's not only the Nash equilibria, but it is also strongly dominant strategy equilibria. That means no matter what the other person is doing, it is always in the best interest for the person to confess, right? So we are all on the same page. Perfect. Okay, so we know that confess is strongly dominant strategy equilibria when and both the prisoners confess. Confusion? Still confused?
Isn't sure about 1, Nash?
Okay, let's check it, then it's okay. So if this person is not confessing, then what should column player do? If it does not confess, it gets the utility of 2. So column are second player. Okay, so if the first person is not confessing, if the second person also not confess, he gets the utility of 2, whereas if he would have confessed, it gets the utility of 6. So that means when the person 1, prisoner 1 is not confessing, then it's in the best response of player 2 is to confess. Agreed? Similarly, when prisoner 1 is confessing, again the best response of player 2, 1 is greater than 0, is to confess. So no matter what the prisoner 1 is doing, NC or C, it's always in the best interest for player 2 to confess. Yes, the same thing, it's a symmetric game, so the same thing will happen to the other player also. Therefore, 1 comma 1 is strongly dominant strategy equilibria, because every time for every corresponding strategy of the other player, this is strictly greater. Perfect. Okay, good. Please feel free to ask questions. It's perfectly fine if you would have missed the other things. Okay, so the question that we are trying to ask is, of course we understand, now this is just the numbers. You could actually play with these numbers and make them much worse. So for example, 2 comma, it may seem that 1 comma 1 is very less than 2 comma 2, it doesn't matter, just the utility of 1, but you can make it really worse. So 2 comma 2, you could make 100 comma 100 and scale up the numbers, but still the issue will be that confess, the utilities that the individual prisoners are getting with confess is significantly lesser than what they could have achieved when they would have both did not confess. Okay, so what we want is to make these prisoners cooperate so that the resulting output is better. Okay. So now what you can assume, because if you have heard the story, we can just say that prisoners were friends earlier before they were caught, and maybe they can sign a contract saying that if we were caught, then this is what we will do, no matter what the police is laying the rules, right. So now what they can do is they can basically sign the contract, and in the contract it will be written that no matter what happens, we will not confess to the police. Okay. And what happens is, of course, the other person, because it's the game that you will come to know later, you will have to lay out the rules for each and every possibility, right. So even though there is a concept of contract signing, there is a possibility that one person does not sign the contract, right. So we assume that if the one person is not signing the contract, the other person will automatically play C, which is the strongly dominant strategy of the player. Does it make sense? So if I want to sign the contract, and if the other person is not signing the contract, then by default I will play my strongly dominant strategy. Make sense? Yes? No. If P1 signs the contract but P2 doesn't sign, then P1 will play C. So it should be if P1 is willing to sign the contract. If I am willing to sign the contract but the other person is not signing, then I will play C. Okay. Okay. Similarly, if only P2, if the other way around also, if only prisoner 2 is willing to sign the contract and P1 doesn't sign the contract, then it will play C. We need this in order to complete basically this table. Okay. So what this table does, it is adding one extra row and one extra column which represent the contract signing. Now the reason that we need these two things is to complete this table. What happens if the other person is not signing? Okay. So if you have this contract signing example again, then again what will happen if this person is non-confess, that means it is not signing the contract, then by default this person, which is player 2, will play the strategy confess. So this particular utility will get replicated here. Okay. Similarly, this particular utility will get replicated here, whereas if both the players confess, then they get both the utility which corresponded to NC comma NC, which is 2 comma 2. Sign. So sign means they will actually, so I am assuming once they sign the contract, they will actually stick to whatever other terms of the contract are. There is no denying from that. Okay. Contract sign, they will both play C, NC comma NC. Questions?
So like in other games, do we consider the case where they might break the contract, like some probability that they might break?
So in game theory, we don't change the rules in between, right? So if they have signed the contract, that means they will admit to it.
If we are replicating the real scenarios, say where they signed the nuclear
So
treaty.
you can always do it, right? So you can have a heavy penalty. You can actually make a legal contract and say that if you break the contract, then this would impose so much penalty that it's not in the best interest for you to break the contract.
Like, do we simulate these things in the game theory the studies that we do in game theory.
So once you understand, the reason that I'm doing is contract signing just represent the cooperation between the agents, and we do see that when there is a cooperation, there is an inherent increase in utility. So even if you see contract signing in this case is at least giving better utilities to both the players, right? So in this game what happens, can you visualize the Nash equilibrium of this game?
Yes. Contract signing.
CSCS is Nash equilibrium. Okay, how do we check that? So if I am at this block, okay, the player 2 is getting 2, so it does not make any sense for him to deviate to either C or NC because he gets something less than 2. Okay, similarly if the player 1 is here, it does not make any sense for him to deviate to C or NC, which is 1 or 0, therefore it will stay till here. So 2, 2 is definitely a Nash equilibrium. Perfect. But what about the earlier Nash equilibrium? Huh? What happened to C, C?
Still Nash.
It is still Nash equilibrium. Okay. So in this game, you have CS, CS is weakly dominant strategy equilibrium, and C, C is still PSNE. Okay. So again, in game theory, it's a huge question that, you know, if there are multiple Nash equilibria, which Nash equilibria will the players play? Okay. So right now we are not going to the question, but just trying to understand what is happening here. Okay. You can just check this. So weakly dominant strategy equilibria is because if
It is going worse, right? If it's not signing the contract, it is going to the
okay,
worst.
so what is weakly dominant strategy equilibria?
Like strongly dominant, the notion for strongly dominant that I have is that if I change my strategy, then I will be worse.
No,
Okay.
so I call a particular strategy strongly dominant strategy. Let's
when
understand.
we go to worse, then it's strongly dominant.
No, it's dominated. I'm talking about dominant strategy. Strongly dominant strategy is a strategy when no matter what the other person are playing, this particular strategy is strictly better for me. Okay. In a weakly dominant strategy, what happens is this particular strategy is strictly better for at least one strategy and equal or better for the other strategies. So in this case, for example, if I consider CS, okay, if I consider whether CS is a weakly dominant or strongly dominant strategy for player 2 or not, okay, so then what will I do? CS should be better no matter what these players are playing. Okay, so if this person is playing NC, then it doesn't matter for player 2 whether it plays 6 or C or CS, it derives the same utility. Okay, if it is playing C, again it derives the same utility. However, when this player plays CS, it derives a strictly better utility. So therefore, CS is a weakly dominant strategy for player 2.
Because
It had equal in CA, whereas for CC, this was not the case in the earlier game. Okay.
So this CC will also be weakly dominant.
CC will not be weakly dominant. It cannot be. Let's see. CC cannot be, right? Why? Because when the other person is playing CS, it's strictly better for this person to play CS. In order to have a weakly dominant strategy, no matter what the other person is playing, it should be better for me. In this particular game, because I have introduced CS as another strategy for the player, I have introduced CS for player 1, therefore when player 1 is playing CS, it doesn't make sense for me to play C. Therefore, C is dominated by CS. Therefore, C cannot be weakly or strongly dominant strategy. Are we good? Okay. Okay, so good. We basically, so we do understand that if the prisoners were to sign the contract, they can actually sign the contract and derive a utility which is much better than 1 comma 1, which they were earlier doing when they were playing with respect to only the self interest, right. Now, what I want to ask is the question, does there exist a contract where they derive a utility which is strictly greater than 2?
Both of them together.
3 comma 3, 4 comma 4 or something, both of them derives the utility strictly greater than. See, if one of them derives a utility better than 2 and other less than 2, there will be something wrong because this is a symmetric game, right. So, does there exist a contract? Can we come up with a contract such that both the players derive the utility which is strictly greater than 2 is the question.
One may get 6 and they both share.
Sorry?
One may get 6 payoff and then they decide to share it.
Perfect. This is the right answer, but in a different
That
sense.
is years in prison, right?
Huh?
That is
Utility, but no, that's not exactly correct. I didn't say exactly correct, but the idea is there. Okay, so the idea is to share. So that means what you can do is, there is a 0 comma 6 here. So one person is getting 6 here and other person is getting 6 here. So what you do, you basically flip a coin and let one person take everything. But that flip coin that you are doing, make it unbiased. So that means make a contract where both the players are supposed to flip a coin, let's say while they are going for a robbery, before that only they are flipping the coin. Okay, you will confess, I will not confess. If the coin is otherwise, I will confess, you will not confess. Okay, it's like you take jail time once and I will take the other time, something like that. Okay, so what you can do with that is basically the following. If the coin turns up heads, player 1 plays C and the other player plays NC. If the coin turns up tails, player 1 play NC and player 2 plays Cs. This is what I mean, different way of telling it. Okay, so you share. Okay, so then what will happen? If this was the game earlier, with the new contract, what will be the utility if both the player signs the contract? Then what will happen? Because there is a coin flipping involved, instead of the dominant utility, you will be now asking for the expected utility. Because the utility now depends on the outcome of the coin. Are you with me? Okay. So, with 0.5 probability, what will happen? With 0.5 probability, player 1 will get a utility of 0, player 2 will get a utility of 6. With 0.5 probability, player 1 will get a utility of 6 and player 2 will get a utility of 0. Therefore, the expected utility of both player 1 and player 2 will be 3, which is better than 2 comma 2. Make sense? Perfect. Okay, good. So, we got one more column and row added, but the idea is similar. I mean, these numbers are basically the same thing if none of them signs the contract, but whether it is a modified contract or the original contract, the other person who wants to sign the contract will always play C. Just to complete this table, we need all the rules. Is it okay?
What is CS? We came very late.
Yeah, so it was, okay, let me just quickly recap. So, we started with prisoner's dilemma game. We basically had the C comma CS PSNE. We were trying to say is that can we make prisoners to basically switch from C comma C to NC comma C. Then we say that you imagine there is a contract. Okay, if the players sign the contract, then what happens is they basically say that in the contract it is written that whenever we get caught, we will play NC comma NC. So, therefore, this is the NC comma NC they will play. So, if they both, so CS is the strategy which correspond to contract signing. Okay. If they sign the contract, they will both get 2 comma 2. Okay. If I am willing to sign the contract, whereas the other person is not willing, then I will play C.
I should confess.
I should confess, that's the strongly dominant strategy for me, right. So, that is why I am confessing. So, this is how we get the table. The next question we asked is, can we make better than 2 comma 2 by some other contract signing? Okay, then we said that imagine a contract where you are basically, it's a random contract where if the coin turns up head, you basically stick to this cell where one person gets 0, other person gets 6. If the coin turns tail, you stick to this cell. Okay. In this case, the expected utility for both the players will not be 2, 2 but 3, 3 because it will become expected. So, with half probability player 2 is getting 6, whereas with half probability player 1 is getting 6. So, it will be 3, 3.
The CS contract isn't still dominant over the 06 or nothing?
No.
Because the person who is ending up with a loss, like 06 means somebody gets
No, so that's what I'm saying. So 1, 1 will still be PSNE. 2, 2 will also be PSNE, but now you have actually introduced one more PSNE, which is 3, 3. All of them will be PSNEs. Now we don't know which PSNE it would converge to, but we are just increasing the we are just increasing the options to the players so that they can get better and better utility. This is what we are doing.
So we are designing more PSNEs with better payoff.
Yes, by making the agents cooperate. This is only possible when the agents are cooperating with each other. This would have not been possible without cooperating. You had a question?
Yeah, so every cell here is written except that 3, 3 is it doesn't. To realize that 3, 3 you have to play this game many times.
You can say that, but so every time you ask, you basically sign this contract CS prime, you basically flip a coin. So yes, because we are talking about expectation, you assume that they are playing many times to converge to 3, 3, but even without that, you just take a random guess, right? I mean, it's just the expectation in that case.
Instead of this, if we say the contract is like player 1 will play C and player 2 will play NC all the times, and then they'll share at the end without the coin being involved.
So sharing is, I don't want the sharing part, right? So that's why I'm saying that although the sharing idea came, it's almost like sharing, because one time I am sharing the jail time and second time you are sharing the jail time. So because the division is difficult, right? I mean, in the game theory, when you're laying out the rules, I'm still talking about my own utility. Okay, then you can always say ki, next, maybe even if contract sign ho gaya, you got the money and then you run away. Okay, so I don't want to get into those. It's just expected payoff. It's like almost similar to sharing.
Like turn by turn taking the jail.
Turn by turn taking. So one time I am taking the full reward, second time you take the full reward, so that we don't have to ever meet again, right? So
This is not a mixed strategy.
this is not a mixed strategy.
It's not independent.
It's
But PSNE is also a mixed
no, we are
strategy.
talking, no, it's pure strategy Nash equilibria, so no mixed strategies. Right now I'm not talking about mixed strategies.
Okay, but a PSNE is a type of mixed strategy in the sense that every one action gets full probability.
Yes,
That way.
that way it is, but in this game I'm only talking about pure strategy Nash equilibria.
But in this case, why would someone play CS prime? In like they're playing only once, like that period of time, okay, it's 3, 3, but if they're robbing a bank, let's say once, why will they choose to do CS prime?
No, because it is with 0.5 probability, at least I'm getting very high reward, right? So I might take a risk, even if they are playing once.
They wouldn't rob the bank again.
They may, right? Who is stopping them not to rob?
This is like a gang. This is operating like
Anyways,
one time thing.
yeah, they can, right? Why should they not? By the way, just the example, okay, just to tell you that, by cooperating you can actually achieve better things. So, just understand the heart of the example, or the intent.
Why is CS not WDS?
CS is not WDSC, it cannot be, because C is the one, C is sitting here. So when this person is playing NC, okay, for this person CS prime doesn't, it's okay. When this person is playing C, everything is okay. When this person is playing CS, this is better, okay. When this person is playing CS prime, CS prime is better, yeah.
I was talking about previously you said C is WDSC and CS is PSN.
That was
No, CS was WDS.
ulta. We said CS was WDSC, C comma C became PSNE, okay. I guess here CS prime will now become WDSC and others will become PSNE because it is deriving better utility. Yeah?
And here also same, right? If someone does not sign contract, I will confess.
Yes, that's the rule. That's how these numbers are coming up.
So the contract would have them drop the bank again, right? Otherwise it will be still 0-6 or 6.
I mean, it's a coin flipping, okay? So you flip it's a randomized strategy. So you flip a coin, okay? Whether you rob a bank again or not, but because you're saying with half probability. So imagine these numbers are very, very high, okay? Let's say it's 0,100. Then with half probability, I'm getting 100 rupees. Okay, that is still better than getting just 1 rupee. Okay, so imagine like that.
But it is like a mixed strategy. It's random.
I don't want to get into mixed strategy because when we talk about the correlated strategies, they are not exactly mixed strategies. So we will come back to it. So don't get confused with the mixed strategies as of now. So because you asked the question, let me clear out the confusion here. What happens in mixed strategy? In mixed strategy, you are assigning a probability to individual strategies, right? So for example, player 2 will say, I will play NC with some probability and C with some probability.
That's independent of the other.
That's independent of the other thing. Whereas in correlated strategy, what is happening? You are basically assigning the probability of each strategy profile. So you are assigning a probability NC comma NC, the probability is 0. NC comma C, the probability is 0.5. C comma NC, the probability is 0.5, and C comma C, the probability is 0. Understood the difference? So the difference is here that in correlated strategies in such game, you are basically defining the probability distribution over the strategy profiles. Whereas in mixed strategies, you define the probability distribution over the individual strategies. That's a major difference. That's why don't get confused with the mixed strategies.
So is it true in general, like if there is a duplicate game, it is one PSN, no matter what column we add, the PSN remains PSN?
I don't think so that will happen. I don't think so. You can, so here we are adding the column with respect to increasing the values. You can always come up with adding another column which changes the PSNE. I don't think that's correct. Shouldn't be too hard.
It will give a reason to deviate.
Yes, it will, I mean, shouldn't be too hard to come up with such an example. So for us, these numbers are not arbitrary, right? So when you add column and row, you can come up with the arbitrary number such that the PSNE shifts. Not a big deal. Yeah. Okay. Are we okay now? Good. So let's come back to the correlated strategies, which I had just explained you in the last slide. So what is happening in correlated strategy is there are two terms. One is correlated strategy, which we will bring, but another is coalition. So when you think about a word coalition, think about that players are basically coming together to develop some strategies. Okay, so these people are basically, coalition is the one, the subset of the agents which decided to cooperate with each other. Okay, so I say C is a coalition which is a subset of the total number of players when they decide to cooperate with each other. Prisoner's dilemma, we basically had the coalition of players 1, 2. Okay. Okay. So now how do I define the correlated strategy? Correlated strategy is nothing but the probability distribution over the strategy profiles of the players in the coalition. Let me repeat again. A correlated strategy is a probability distribution over the strategy profiles of the players in the coalition. In this example, the correlated strategies, so first of all, what was my coalition? My coalition was both P1 and 2. My C was 1, 2. Both the prisoners are cooperating with each other. And what is a correlated strategy? Correlated strategy will be the probability distribution over C, 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 NC, NC, C and NC, NC. So, any probability distribution over these 4 profiles would be what? My correlated strategy. Whether it is giving good utility, bad utility, does not matter. Okay. So, correlated strategy will be the probability distribution over these strategy profiles. So, when I talk about my contract signing first, right. So, in the first CS, right. So, what I was doing in CS, what was the probability distribution? It was nothing but I was assigning 0 probability to C, C, 0 probability to C, NC, 0 probability to NC, C and 1 probability to NC, NC. So, contract signing, the first contract that we saw was also a correlated strategy, where both the players end up in playing NC, NC. This is the strategy profile that I am choosing. Similarly, when I checked for CS prime, okay, what was the correlated strategy corresponding to CS prime? It was 0, 0.5, 0.5 and 0. Okay. So, any distribution over these strategy profiles will be correspond to a correlation strategy. Are we on the same page? Okay, good. Okay. So, I will denote, so now you understand the difference. So, if I expand this SC, it will be Cartesian product of I belongs to C SI. Okay. So, it is a simplex over the Cartesian product, whereas what is mixed strategy? Mixed strategy is Cartesian product over the simplex. Okay. So, in the mixed strategy what you have, when I say sigma I to be mixed strategy. So, if I say sigma I comma sigma minus I, this is the mixed strategy, right. So, then what is this? This is nothing but this is what? This is Cartesian product of delta SI. Okay. So, for each SI you define a probability distribution and then you take the Cartesian product. So, this was your mixed strategy. Okay. Please let me know if I should take the examples, okay, if it is not clear. Yeah, this we have already done. So, tau C is you take the probability distribution over the Cartesian product and sigma C is you are taking the distribution and then taking the Cartesian product. Okay. Okay. I think this is also we have done, just written. Okay, we can do. Okay. So, this was, yeah. Here.
What was SC again? SC was Cartesian
SC
product of-
is the Cartesian product of SIs where I belongs to C. So, it is the it will become clear in the next example. Okay. So, in my prisoner's dilemma case, C was what? 1, 2. Okay. So, SC is a set of all possible strategies profiles, right. So, SC will be C, 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 NC, NC, C, NC, C. This is my SC. Okay. Now, tau C is a probability distribution over this. We understand this, right. Whereas, if I want to see sigma I comma sigma minus I, let us take an example. So, suppose I want sigma 1 comma, how the mixed strategy will look like here? So, what will sigma 1 look like? It is the mixed strategy of player 1. How will it look like? It will give some probability to C and some probability to NC. Right? Let's say 0.5 to C and 0.5 to NC. Okay. Similarly, how will sigma 2 look like? Let's say 0.2 to C and 0.8 to NC. This is sigma 2. Then what is your mixed strategy? Mixed strategy is basically Cartesian product of sigma 1 and sigma 2. Okay, it is sigma 1 comma sigma 2, where sigma 1 could be any mixed strategy and sigma 2 could be any mixed strategy. Whereas correlated strategy is the Cartesian product over the strategy profiles. Okay. But from here you can actually tell at least one thing. If I have this mixed strategy, okay, if I have this mixed strategy, then it corresponds to some correlated strategy.
Then multiply the probability.
Just multiply the probability. Okay, so C comma C, so if I want to convert this sigma 1 comma sigma 2 as the mixed strategy to the correlated strategy, then what will you do? You will find what will be the probability of playing C comma C. And what will be the probability? It would be when player 1 is playing C and player 2 is playing C. Because they are playing independently, so this will be 0.5 into 0.2. That would be C comma C. What will be C comma NC? This will be 0.5 into 0.8, which will be 0.4. Okay, NC comma C 0.5 into 0.2, which will be 0.1, and finally 0.4. Okay. Sigma 1 is a mixed strategy of player 1, sigma 2 is the mixed strategy of player 2. Make sense? I will give you some time to think. Are we good? Okay. So we just saw for two players. Okay, I just want to just convey one thing, that it is not always necessary, because this will be required for our coalition games. It's not always necessary in a game that all the players are coming together to cooperate. Okay, in a two-player game, cooperation mean only when both the players are coming together, right? But when you extend it to n players game, let's say 3-player game, it might happen that one is not cooperating, but 2 and 3 are coming together and cooperating. That's possible. Okay, so in this case, for example, if I have n is equals to 1, 2, 3, if this is the strategy sets and C is equals to 2, 3, remember C represent my coalition. Coalition mean in this particular example only player 2 and 3 are coming together to cooperate. One is playing something else. Okay, so in this case SC would be basically all possible the strategy profiles of over x2 and x3, okay, over s2 and s3. Okay, so this would be the strategy profile, and what will be the tau c? Tau c will be the probability distribution over each of these profiles. Is it clear? Okay, good. Okay, now when you want to find the expected utility of a player, okay, how will you find the expected utility of a player? So I have a game where I have 3 players. The strategy set of player 1 is x1 comma y1, strategy set of player 2 is x2 comma y2, strategy set of player 3 is x3 comma y3. I have a coalition C, okay, they can form a coalition, and then because they can form a coalition, I can define something called the correlated strategy, which is nothing but defining the probability distribution of over the strategy profile of the coalition C. So far so good. Okay. Now what I want to do, I want to define the because it's a probability distribution, I can only talk about the utility in expected sense. So, I want to find how will you compute expected utility of player I when player 1 is playing x1 and player 2 and 3 are playing with respect to the correlated strategy. Is the notation clear? Perfect. How will you find that? It will be summation over all these strategy profiles in SC. You will multiply this probability with the utility of x1, x2, x3. This probability with utility of x1, x2, y3. This probability with x1, x2, z3 and so on and so forth. Make sense? Good. This was easy. Similarly, you can compute y1. Now, here x1 will be replaced by y1. Okay, and this is the shorthand notation. It might help if you write in your notebook with the notations. I can take the break whatever you want.
So this is like conditional utility given that player 1 is playing x.
Yes, so when you, so if you want to make a table again, I mean then what will be the utility of player 1, player I when one is playing x1 and others are playing with tau c. It's similar to how you define utilities, but in the game definition you are given a table which represent the utilities correspond to only pure strategies like we had earlier.
Player 2 playing some strategy, then I would have to restrict tau c and
No, so only utilities will be correspond to x1 and tau c because we are assuming 2 and 3 are playing according to tau c. So now you cannot ask, I mean when they are playing according to tau c, then it doesn't make any sense to ask what will happen if player 2 is playing x2 for example. You are assuming both x2 and x3 are playing according to this correlated strategy.
So expected utility of player I which doesn't belong to C. If it belongs to C, I guess we have to talk about something.
No, it would be same, right? So again, so when you say x1 comma tau c, what does it mean? So when I say ui of s1 comma s2 in a two-player game, what does it mean?
Utility of player 1 is x1.
So utility of player I when player 1 is playing s1, player 2 is playing s2. Okay. Now I am talking about ui of x1 comma tau c in this case, where c is my 2 comma 3. So in this case what is happening? You are basically saying what is the utility of player I when player 1 is playing x1 and the other players are playing according to tau c. Yes, if you want to still so when we completed table, like contract signing was also correspond to tau c, you can still ask ui of x1, x2, x3. That's perfectly okay to ask. But this is easy. This was already there in the table. What was not easy is this. Okay. Yes, that's called the grand coalition. So everything is possible. It could be small coalitions or it could be a big coalition.
Just to confirm, there can be many disjoint coalitions.
There could be many disjoint coalitions, yes. There could be. For this I am not, there can be, but I am not so sure. I haven't seen. Matlab, right now I'm not considering them at least.
Like one guy can play from both sides.
I mean, it's difficult because the way we are saying, I don't think there could be, or cooperative game theory should allow the non-disjoint coalitions, because eventually you are defining the probability distribution over the strategy that the players are playing. So if one person is in the two coalitions and the probability distribution is completely different, then what will this person do? There will be the issue, right? You cannot implement that correlated strategy.
So, but there could be many potential coalitions in the sense that at a time, a person can be only part of one coalition.
Yes, but there could be multiple potential.
Like over
So you
two,
can
three,
also,
1, 3.
I mean, you can, right? So for example, you can, instead of 1, 2, 3, you can have players 1, 2, 3, 4, and you can talk about coalition 1, 2 and 3, 4. In this case, you will define, let's say this is C1 and this is C2. In this case, you will define a probability distribution over tau C1. You will define a probability distribution over tau C2. Okay, and then you can talk about the utilities of 1 with respect to tau C1 and tau C2.
Okay, but here the coalitions are disjoint.
That coalitions are disjoint, but what I am saying is I don't think that a non-disjoint coalition will make sense, because imagine if you have 1, 2, 3 and let's say you have C1 is equals to 1, 2 and C2 is equals to 1, 3. Suppose.
So is there a notion where while I could be part of many different coalition and my utility function would be different, but while playing a game I have to declare which coalition I am part of and play the game from that point onwards just with that coalition. So once game
But
is started,
that-
I don't change, I can't make, like I am part of this coalition as well as that doesn't matter.
So the way the cooperative game theory works is the following: you have the game, okay, you define the game, and let's say you have all possible coalitions that are possible. So typically how the thing work is, which coalition is best for me to be the part of, because game is already defined. You can find your utility if I become the part of this coalition. Okay, we will discuss correlated strategy equilibria. You can find correlated strategy equilibria, let's say, and then you see, you know, if I belong to this you can actually
It's an ordering on the quality of coalition. Like I know what is the best coalition.
exactly. Then why would I? So I'm saying that why would I belong to part of two coalitions? Yeah.
We were saying about this.
Sorry,
C1, C2,
what?
If they are in both,
So that's what I'm saying. I don't think it's allowed. Mostly it's not, because what will happen is, with respect to this, I will get some correlated strategy tau C1. With respect to this, I will get some correlated strategy tau C2. Okay. Now so how does tau C1 look like? So if let's say I have x1 y1, x2 y2, x3 y3. These are the strategies of 1, 2, 3, right? So then tau C1 would be what? It would be a probability distribution over x1, x2, x1, y2, y1, x2 and y1, y2, right? So this would be tau C1. Similarly, tau C2 will be what? x1, x3, x1, y3, y1, x3 and finally y1, y3. Okay, and there are some probability distributions associated to it, and whatever the probability distribution is, they could be very conflicting of each other, right? So for example, this has, let's say, 0.5 probability, okay, and this has I don't know, let's say 0.2 probability, whereas this one has 0.1 probability and this one has 0.1 probability. Okay, now imagine what will player 1 do. Okay, so you want to implement both tau C1 and tau C2 together.
We don't have to allow that.
So
That's
then
the
how
thing.
will you do?
So you say that player 1 can only has to declare its coalition. Once it sees what it is C1 or C2.
That is okay. That is okay.
It declares.
Otherwise,
it's when I am part of coalition C1.
That is okay.
So that tau C has to be declared clearly.
Yes. So, but what I am saying is, why to even get confused? Let's assume, because in order to have a well defined game, You have to belong to only one coalition. So let's not allow to be in a multiple
But
coalition.
like, say, I can define a game. Say there are three people,
Hmm.
and they have to hit each other to get points.
Hmm.
So then, if one player says that I am in coalition with you and I am in coalition with you, so he hits both the players and he gains.
So game theory is a course of ethics, right? I mean, once I've said that I am with you, then I am with you, okay?
They believe that he is with them.
There is no belief. This is a set of rules, okay? If it is known that player 1 and player 2 are coaliting, then they are coaliting. End of story.
They are coaliting.
But then 1 and 2 can,
1 and 3
1 and 3 cannot coalesce, right? So if it's done, I'm just coaliting with one person, okay? Or maybe one group. Let's stick to this, okay? Anything else? Okay, so the next concept is about the grand coalition, right? So grand coalition, we know that is nothing but the set of all the players. So this is the grand coalition. So I say that a particular coalition is a grand coalition when everybody is cooperating with each other, okay? And what is the expected utility of the player I under correlated strategy? It is nothing but alpha S UIS, where alpha S is S is coming from the strategy profile of all the players. Alpha S is the probability that you are assigning to it, and UI as the utility corresponding to that strategy profile. Okay. We have already done this. Any correlated strategy alpha can be implemented by a contract. You can basically go to your coin tossing example and then just implement it, because it's just nothing but the assignment of the probability distribution over the strategy profiles, and the expected payoff allocations also you can do, okay? Are you with me? Okay. So now this is important to see, because so what do I mean by this? The set of expected payoff allocation is nothing but, it basically is the set of all possible utilities that players can derive by playing any correlated strategy, any possible correlated strategy. Okay. Let us try to understand this, and this set will be closed and convex subset of Rn. First of all, do you know what is closed, what is convex? Okay, what is convex?
When you take 2 points in the set, the path between them is in the set.
Exactly. So, can you see why this set will be a convex set?
Before that, so n is the, what is n?
Oh, this should, n is the total number of players.
Oh.
So that means if we take any two expected utilities and we take a number between those expected utilities, we'll be able to form a coefficient as well as a probability distribution such that the expected utility for that would be the same.
Perfect. Definition is correct. But how do you prove this set is convex?
So we have to find that. In order to prove, we have to find this.
Yes, but it's easy, right? So if you really think about utility, so first of all, utility is a linear function. It's just the expectation, right? So if you have two correlated strategy, alpha 1 and alpha 2, okay, so you will have expected utilities corresponding to alpha 1 and alpha 2. That would, both of them will lie in your set, okay. Now what you do, you basically define any point between this line, okay, you find the correspond, so you basically for any lambda, you find lambda alpha 1 plus 1 minus lambda alpha 2, okay, find the expected utility correspond to that. So that would be basically the point that you want.
That's also linear function.
That's also linear function, okay. Prove this. Do we know how to prove whether the set is convex or not? Huh. That's why it's this convex. So prove this. So today I will have more tutorial questions than yesterday. Okay, great. We'll come back to this. I have already given you this homework. Okay, so now the next topic that I want to cover is, so what we have seen so far, we have seen how to make people cooperate by defining some correlated strategies on it, right. So now the question that I want to ask, why will people even go to correlated strategies? When will people cooperate with each other? They see that their utilities increase. So that concept is captured by what we call as the individual rational correlated strategies. Okay. So what are individually rational correlated strategies? Individual rational correlated strategies are those correlated strategies which are giving at least the security value to the agent, which are giving the utility which is at least the security value of the agent. What is security value of the agent? Max min value. Okay. So I know that if I would play individually, I can at least derive my max min value. We know what is max min value is, right? Okay. So when I play individually, I know that I can derive the max min value. So whatever correlated strategy I am asked to play, I should at least get this much, right. And that this leads to the definition of individually rational correlated strategies. So all those strategies where the utility, all those correlated strategies where the utility is at least 1, because 1 is the security value, again a homework, 1 is the security value of the agent here, will be individually rational correlated strategy. Make sense? Okay. Yes, please.
This is true for even general games.
Yes.
More than 2 players.
So in general game you can still define the correlated strategies, max min value. The only thing is in general value the minimax theorem will not hold.
So what, then how do we define this?
This is a simple definition, right? So
we just take this value, max of min.
yes, exactly. This is so okay, let's quickly recap what it means. It means that suppose a player, so what I am saying is, suppose I fix my strategy as sigma I, okay. This particular value is finding what is the minimum utility I can get corresponding to sigma I. The inner loop is basically telling what is the minimum utility I will get corresponding to playing sigma I. Yes, I find such minimum values for all sigma I, okay, and I choose to play that sigma I which is maximizing this minimum value. That means what? If I play this sigma I, no matter what the other person is playing, I am guaranteed that I will get this much value. Does it make sense? Okay. So that means if nothing thinking, if I would have just stick to sigma I, then this much utility though I would have guaranteed. So individually rational correlated strategy mean the correlated strategy which give me at least this value.
Correlated strategy, that is WDSC.
No, that's different.
Meaning it's no-brainer to play that strategy.
No, that's completely different. Don't get mixed up with WDSC. WTSC is a very strongly dominant,
May not even exist, right?
may not even exist. For the games that we are talking about, individual rational correlated strategy may exist, but WDSC may not even exist. WDSC is completely different.
Can you give an example of individual rational?
We will come back. So individual rational, even in this particular example, individual rational correlated, so here the V1 lower bar and V2 lower bar is 1 comma 1. 1 for player 1 and 1 for player 2. Same thing. Just told you, right? So, if the person is playing sigma I, you find what is the minimum value that I will derive. What is the minimum utility I can get? Okay. So, if I play NC, the minimum utility that I can derive is 0. If I play C, the minimum utility that I can derive is 1. Okay. So, then I maximize my minimum utility. Okay. So, in this case my Vi lower bar will be 1. It is not mixed strategy, but in this case it will be. You can.
No, but like in the definition, they use
In the definition it is mixed strategy, but right now I am giving you the example with pure strategy. Okay. Okay. Similarly, here also the same thing, 1 will come. Okay. So, 1 comma 1 are the security values of prisoner 1 and prisoner 2 respectively. Okay. So, individually correlated strategies will be all those correlated strategies which are deriving values at least 1 comma 1. For example, whatever we discuss CS and CS prime, both are resulting in individually rational correlated strategy. Whereas, what is not individually rational correlated strategy? If I put, let us say, what is not, if this for example 0 comma 0 comma, sorry, 0 comma 1 comma 0 comma 0, just some arbitrary. So, if you just say that you put all the weight to C comma NC and everyone else gets 0, then it is not individually rational correlated strategy for player. Yes. Okay. This is how you plot the things. Okay. So, in our prisoner's dilemma example, if I see the blue triangle, okay, this corresponds to all possible correlated strategies. Okay. It is just nothing but the convex combination of 0 comma 6, 6 comma 0, 1 comma 1. Okay. And 2 comma 2 will be somewhere here, which is your NC comma NC. Okay. And this will be a convex set, please prove it. Okay. Now, what will be the individually rational correlated strategies? Individual rational correlated strategies are those correlated strategies which are giving at least utility of 1 to each player. Okay. So, that means it is this orange triangle. All these strategies here are individually rational correlated strategies. This will also be a closed and convex set. Prove this. I can still make one set here and one set here, right? So, that is not the definition of convex. Okay. Okay. My last concept is something called the correlated strategy equilibria. Okay. When do you say something is equilibria? Any equilibria? No intention to deviate. It's as simple as that. So, what do you think, what will be correlated strategy equilibria? No intention to deviate from this strategy, right? So, it's the same thing. A particular correlated strategy is called a correlated strategy equilibria in a very, very informal way. If there is, for any player in the coalition, it is in his best interest not to deviate. As simple as that. Not to, sorry?
Play that particular toss.
To play that particular tausi. Okay. What does it mean? It means the following. This may be slightly tricky. So, what is UI alpha? UI alpha is the expected utility of player I by playing the correlated strategy alpha. Okay. we know the expression of this, sum over S alpha S into this thing. Okay. What you want is, so when I am talking about unilateral deviation in the correlated strategy and alpha is the correlated strategy, that means I am assuming again single player deviation. That means all the other players in this coalition are playing according to alpha. I am just thinking whether I should deviate or not. Okay. So, that means when you take the probability distribution, it is alpha Si comma S minus I. Okay. And what is this? Di is a function which is denoting the deviation. So, when I say Di of Si, this could be any other strategy. Okay. So, Di is a function from capital Si to Si. Okay. So, Ui of D comma Si comma S minus I denote the utility of player I when he would have deviate from Si, whereas the other players are playing according to the alpha.
What does alpha Si comma S minus I mean? It means I is also playing at small si.
Nahi. So, alpha Si comma S minus I is the probability that you are assigning to the strategy profile Si comma S minus I.
Correct.
Okay. So, in this particular case, let us say I am talking about CS prime. Okay. So, then what does it mean? It means that with point, so C comma C co it is 0, C comma NC co 0.5 and so on and so forth, right. So, what it means is that 0 ke corresponding to it will cancel out. So, let us talk about this. So, with 0.5 probability, you know that other person, the second person is playing NC and you are supposed to play C.
Both
But
of us are doing this by probability 0.5.
ideally they should be, but let us say I am talking about player 1. Should he play with 0.5 probability, should he play C? That is what I am asking. So, let us say you toss a coin and it turns up head,
Yes.
and you know that you are supposed to play C comma NC. But then I say, let me see, if I do not play C, if I play NC, what happens?
So probability
Okay.
of saying
So,
that
then
utility of
with 0.5 probability, if I deviate from C to NC, and let us say I am here the same, this utility should be less than or equals to if I would have stick to this contract.
So my only question is, instead of that alpha Si, shouldn't it be alpha DISI?
No, because your probability distribution is still coming from alpha.
That's the idea.
So, again, remember from the contract signing, once I have signed the contract, the terms of the contract are same. You are tossing a coin, with that 0.5 it turns up head. Now you are deciding whether should you deviate or not.
So the right hand side here, shouldn't it represent what would have happened to player I had he deviated to DI?
That is what it is representing, right?
So therefore, so the right hand side should be the expected utility of the player I if he is the person who deviates. That's what the right hand side should say. And
No,
that it can't be greater
but
than
the other people are still following the correlated strategy.
Correct.
So then alpha, if you are making this DISI, then it does not make any sense, because it is the probability distribution over the strategy profile. So what you are saying is the following, let me try to say what you are saying. So let us say you are talking about this strategy profile, whether it is a correlated strategy or not. Okay. Now what you are saying is, instead of C, you make this person NC. But now because this is NC, instead of alpha you should consider NC comma NC. Then this becomes 0. But the other person, right, it is still thinking this person is playing C. I mean, it is, this contract is being implemented. So I will still do alpha. Okay. So here,
Okay, my only confusion is, if I look at the problem that alpha as a distribution that everybody is playing according to their contract that they have signed, then the utility, if we compute the utility where the agent I has deviated to something else, then the product of that utility times the probability that they are actually implementing the contract what does it even?
No, so think in this way, okay? So contract signing के जगह you take a moderator, okay? So because the job of the moderator is to make people cooperate among each other, okay? Now because I'm the moderator, I want people to cooperate with each other, and I know that if they cooperate they can come up with better utility, okay? So now with respect to that I basically devised a correlated strategy alpha, okay? And I know that I will just implement alpha. Now how will I implement alpha? I have this probability distribution. I will just tell each of the player that with this probability you play this strategy. That means if I am implementing alpha, the moderator will say with 0.5 probability, it will say with 0.5 probability, if it turns head, then I will say player 1 to play C and player 2 to play NC. So now player 2 is playing NC, okay? But what player 1 is doing, instead of C it is playing NC, but the moderator has said that you play with 0.5 probability C comma NC only. So the probability should not change here.
Okay. Yeah. The enforcement. Okay, I'll try to think about it.
Okay.
Yeah, it is physically how to interpret this thing, like alpha of the contract.
So physically it's like if the moderator has asked the players to play this, then instead of playing this you are playing something else. That's all. Because the moderator is telling me to play something only with probability alpha Si comma S minus I, this remains unchanged.
Yeah, that's the point.
I mean, we can interpret it as playing the game a large number of times. So next time, if in another case, the player wouldn't play NC again. It would play only C for 0.5 probability, because the NC in the distribution is 0.
No, her question is different. So she is saying that why there should be alpha Si comma S minus I. So what I am saying is ki because the moderator is still telling you to play something with this probability, this won't change.
So I as a deviating person, am I not trying to see what would have happened if I deviate from my agreed upon coalition and do this deviation thing?
No, because others are still following alpha, so you can't.
Right, so shouldn't I look at alpha DISI comma S minus I? So we are still doing the contract alpha, but I individually have deviated to them. So यहाँ पे what would that be is like, yes, I changed to C to NC as a first player. So basically both of us are now.
So what you are saying is alpha of NC comma NC.
Yeah, which in this example is 0.
Okay.
So it basically means that none of us get anything. No utility is derived because the probability of this is 0. That term will contribute nothing because I am deviating from C to NC.
This will.
That's a good reason for me to not deviate.
Let me think about it. How do? But matlab, my main thing is let me think about a better explanation. But the explanation is that only ki other players are still following alpha, and if moderator is asking me to follow this, what happens if I deviate?
Like it happens sequentially. When we go into this SI,
No,
then I will choose to go to other strategy. So then that utility
exactly.
comes.
So once the moderator has told me to play this, instead of playing this, I am playing something else.
Yeah, this is unilateral deviation from my part.
From my part only. That is the key point here. But let me think of a better explanation, okay? Okay. So this essentially mean, DSI I can replicate by any other SI prime. So this essentially mean what you want is this. Okay, so alpha I Si comma S minus I into Ui Si comma S minus I was nothing but Ui alpha. Okay, you take this term this side, okay, and DSI is any other strategy. Fine.
Every time moderator asks you to do something, then you change to one thing, like this relation is fixed.
I think I have an example. Yeah.
So whenever he says to do NC, you always do C when you are deviating.
Yes, something like that. I have an example, but I have too many things before that. Let's see. Okay, this we have already done, that every mixed strategy profile. I'll come to that example, then it will be slightly more clear. Okay, so every mixed strategy can be correspond to a correlated equilibria. Because we saw that every mixed strategy can be implemented by the correlated strategy. Okay, so that means every mixed strategy Nash equilibria is also a correlated strategy equilibria. हाँ चंदू. Yeah, okay. So every mixed strategy profile correspond to some correlated strategy. This we have seen. Just multiply.
How do we show this? CS dash. How do we show it from two mixed strategies? In one of the example, we showed that 0.1, 0.4, 0.1.
So I am not saying reverse. I am just saying that if you have a mixed strategy, then it corresponds to something correlated strategy. But every correlated strategy cannot be converted to a mixed strategy. That's correct. Okay. So then by definition, it's not so easy. Okay, you still need some non-triviality inequalities using the definition that we do, but it's not so difficult also to prove that every mixed strategy Nash equilibria will be a correlated strategy equilibria. Not too difficult. Just use these two, this thing and the other equation, you will get it. Okay, so every mixed strategy Nash equilibria is a correlated strategy. I leave it to you. Okay, and therefore every finite game will have at least one correlated strategy equilibria. This is directly coming from Nash theorem. Okay, now the question is more difficult. The question is, how do we compute the correlated strategy equilibria? Okay, computing is not so simple. If you directly go from the definition basically implies that whatever alpha, so when you say how do you compute the correlated strategy equilibria, what does it mean? It means that you need to come up with these alphas, okay, which is a valid probability distribution over the strategy profiles. Okay, so you need to come up with these alphas. So you want to find the alpha which satisfy these inequalities. And how many such inequalities will be there? It will be these many. Are you with me? Okay, and then you will have additional constraints, which is the non-negative constraint, because alpha denotes the probability and the sum should be equals to 1. Okay, if you are able to solve this linear system of equation, you get something which is correlated strategy equilibria. And these are all linear system of equations. So again, not a hard thing. Okay. Okay. Again, just an example. I'll pass the slides and you can just work out the things. Huh?
Summation across the SIs.
Which SIs?
So this is still S minus I.
Yes. So this
individually for every, right? It's not something that holds for all the.
Right, because if I am basically asking whether it is beneficial for me to deviate. So for every individual, for ith player, is it beneficial to deviate? Then I will have
every individual realization of SA also.
Exactly. So for every, so for example, C comma NC, should I, instead of C, should I play NC? For every, when mediator is saying to play NC comma C, should I deviate from NC to C? For every realization I am asking.
So a weaker version of this would be to actually sum across all the SA also. I mean, these things can deviate a bit, but then overall if I sum across all the alphas, then I mean, see the mass here will not sum to 1, right? Because it's seeing only the.
No, it won't, because it's only seeing the S minus i's. Yes.
If I can sum outside over SI, then that mass is 1. So then that means that internally you can become negative, but that's a bit weaker. That's not something we are.
But does that correspond to a reasonable
Correlated
yeah.
equilibria? No.
I'm just trying.
No.
Yeah, the moment we make summation to it, something can be very high, something can negative. They balance each other.
So I can still deviate within the individual profiles, but you're
Some
saying that
degree you are just
in expectation I won't deviate, something like that.
so still your this is still about the conditional probability of having fixed one action from the other player.
Yes.
Then the probabilities that you see for the S minus.
So this is for only one coalition, right? So yeah, is there any
You can extend it to multiple coalition, not an issue.
like notion as the most dominant coalition? Like this is the most dominant coalition.
What do you mean by most
Like
dominant?
there can be many coalitions possible, and which one is the most dominant coalition?
So what does most dominant mean?
Like utility is the highest in that
whom?
coalition
For whom?
one single player. Like from viewpoint of one single player, he has multiple options for coalitions, and then he will compare between all.
So again, we will assume that because one person is forming a coalition with only one group, we will assume that whichever coalition, so this is also called stable coalition, by the way. It's like there is no incentive for me to move from this coalition to the other coalition. Okay, so we will stick to stable coalition domain.
I think those things are studied in hedonic games where people are trying to create whole other coalition. Who will do
I need to understand. Yeah, we were actually working on something, and somebody pointed out that I should take a look into the literature of hedonic games. So, similar concept, right? So, when should people, there should be no deviation of basically changing from this thing. Yeah. There is some interesting things going on there. So, yeah. Okay. So, okay, I don't know. Okay. So again, what should I do? Should I leave it for the homework? Everything is clear so far, right? Okay. So now let's continue. We discussed these contracts, and one of the contract which we discussed was CS prime, which was giving the utility of 3, and we want to ask whether this particular thing is a correlated equilibria or not. Okay, just to make you understand what do you mean by correlated equilibria, I want to find whether this inequality is satisfied. Okay, how do we do that? So, this is alpha ISI, which is 0.5 into, so for others it will be cancelled, right. So, what you want to do, so the left hand side will be what? 0.5 into utility of player 1 C comma NC and plus 0.5 into utility of player 1 C comma C, NC comma C. I will do minus later. Just trying to tell you some intuitions. Okay. So, this is the expected utility of player 1 by implementing the contract CS1, okay, CS prime. Now, I want to ask whether this is a correlated strategy or not. What do you think? Just look at this equation. Player 1, so C and NC. Remember the game table, yaad hai?
In one of the situation it will be 0, so it is better to switch to something where it's
Exactly. So, in this particular situation, the utility of player 1, this particular thing is 0. Okay. So, when the moderator is asking this player to play NC, comma C, it does not make any sense. Okay. This player will basically deviate towards C and make a better utility. So, it is not a correlated strategy equilibria. Okay. Perfect. Okay. Unfortunately, with correlated strategy equilibria, our whole problem of prisoner's dilemma does not get solved. Okay. Because if there exists a strongly dominant strategy equilibria, again not difficult to prove that there exists only one correlated equilibria where you are putting every weight, the entire weight on that strongly dominant strategy. It is coming directly because of this equation. Okay. So, imagine there is something called strongly dominant strategy for each player, then this inequality, if SI prime is strongly dominant strategy, will always be negative. So, I can always change it, right. So, not too difficult to see. Okay, but then why are we studying this?
Maybe it doesn't exist.
Correlated strategy equilibria will exist.
But the strong dominant.
Strong, okay, good. So, but strong dominant strategy equilibria doesn't always exist, and maybe it gives me some good things in the other games, right. So, with this, let's do one more example, I guess 5 more minutes, very simple example. This is called traffic control game. Now, in the traffic control, the rules are pretty simple. I think you would have seen it. There are 2 strategies. So, imagine there is a junction. You have 2 cars, one from this road and one from this road, and if both of the car basically come together, they collide and they both get the utility of minus 10 comma 10. If one stop, the other goes, then the person who is going gets better utility. If both of them stops, nobody is getting any utility. This is okay, right. Now, what are the PSNEs of this game? Quickly. Oh, sorry. Sorry. Arey yaar. Okay. What are PSNEs? No, definitely.
No PSA.
There is no PSNE. Let's try to see, okay, PSNE. Suppose go comma go. I want to find whether go comma go is a PSNE or not.
Second player might go to stop.
Hmm?
Second player can deviate to stop.
Second player can deviate to stop. Perfect. So, go comma go is not PSNE. Let's see go comma stop.
It is.
It is. It is PSNE. Okay. Stop comma go. This is PSNE. Okay. This is not PSNE. Okay. So, there are 2 PSNEs, and what happens in the traffic game? So, if there are these 2 PSNE, one person is getting 0, the other person is getting 5, then you can't just go and stick to one PSNE, right. So, in such cases, the role of mediator helps or the correlated strategy helps, and this is what happens in the traffic signal. Okay. So, a simple correlated strategy will be 0.5, 0.5. In this case, what you can also prove is that any unfair kind of correlated strategy, that means any probability which you are giving here and 1 minus beta here, all of them will be correlated strategy equilibria. Not only this, which seems to be very, very fair, but everything else will be correlated strategy equilibria. Okay. Again, the set of correlated equilibria is convex. Are there any other correlated equilibria? No. Okay. This is just a simple thing. I will skip this. Okay.
Shweta,
Hmm.
it's a correlated equilibria or PSNE? No, is PSNE a correlated equilibria?
PSNE should be correlated equilibria, yes.
Excuse me.
Yes, please.
Why mentioning every time that this set is convex or closed is important in this context?
It's important, right? Why? Anybody else who wants to answer? Why do we say that something, why is it important that something is convex?
Those 2 cannot.
Huh? So, convex property is important when you are trying to find something, some optimal point, right? If a set is convex, it's a well-defined set. So, you can basically make, sorry, you move around. You have a flexibility of moving around and without going out of the set. It's a good property to have.
So you can, the set, if it's feasible point, make a convex set. You know the optimum lies somewhere in it. You can start from a feasible solution and have the hope of moving around and getting to the optimum.
But then closed set, we are also saying that that is closed. Then
The closeness is a different thing. It's like an idea of a boundary condition. But convexity allows you to go from one solution, feasible solution, to another feasible solution. Yes. Right? So that's the thing. Searching. Searching becomes more effective. You'll never jump
You
out
have
of the set.
better algorithms in optimization when the set is
is
convex.
it like a standard thing to mention?
Yes. Okay, so the next question that we want to ask is that we have seen in the last example, in the traffic example, you had too many correlated strategy equilibria. The question that we want to ask is which correlated strategy equilibria is a good correlated strategy equilibria, and what properties should we look into the correlated strategy equilibria.